Hi, I'm John Shook, and this is the first video entry for my Hackaday prize entry, the remote water consumption display. As I said in the outline, basically what I want to do is put a sensor by the water meter out by my street and have a real-time display inside my house, so I have much faster feedback to how much water I'm using, and hopefully can reduce our consumption and maybe even spot problems before they come up. Like I said in the introduction, the text on the page, I have nothing built yet, and this project is going to document the entire process from initial design all the way through to the final unit. So I figured I'd start here by just doing a simple block diagram of what I have in mind. So out by the street we have the water meter with the little dial assembly on the top. We need to put a sensor on there that can detect the rotations of the stuff inside the meter. So we have a sensor. We need to go to some sort of microcontroller that's going to read the sensor and send the data back to the house. For that, we're going to need some sort of a transmitter. Back on the house side, obviously, we'll need a receiver that's going to receive that data, give it to another microprocessor that's going to have some sort of a display. Additionally, what we need to do from the microprocessor is have a link onto the internet, because if something goes terribly wrong, I want to know immediately from this system, and periodically I'd like to get a tweet or a text or something that says, here's your consumption for the day or for the week, or are you above or below targets or whatever. So we're going to need some sort of an interface to the internet and throw the data out there on the cloud, and from there we can go to Twitters or emails or whatever we need it to do. Over at the sensor part of the problem, or a design challenge, is that we're about 50 feet between the water meter by the street and the inside of the house, and there is no electricity out here. So what we're going to have to do is put a photovoltaic panel and some sort of a battery pack to power this entire thing. I've sourced most of the parts for the initial try here. Starting with the sensor, inside the water meter, there's a brass body that has the moving parts, the gear. It's a positive displacement pump that actually measures the water flow through. In a separate plastic element is all the gear drives and the dials and the displays. Between these two are a couple of very strong super magnets. The reason they do this is the magnet associated with the brass part is inside the enclosure. There's no penetration, so there's no seals. It can never leak. The associated magnet is up in this plastic part, which is a hockey puck, which can be removed from this brass assembly. The reason they do that is, again, there's no seals, the thing can never leak, and if something goes wrong, odds are what breaks is inside this mechanical thing with all the gears and dials and displays. They can just remove that plastic part and replace it without having to disconnect any of the plumbing down there. Now, my sensor, what I want to do is detect these two super magnets, which are bound together by their magnetic field, and convey the rotation into this meter assembly. Online, I found a couple other projects that tackle this that use standard Hall effect sensors, the little 3-pin guys. The issue with that is the Hall effect sensors are made to go inside motors, detect shaft rotations in motors, detect magnets on moving things. They are not really sensitive because they expect a fairly large magnetic field that they're going to do. The part I chose is a 3-axis digital magnetometer, which sounds pretty impressive. Basically what this is the compass chip that's inside most cell phones today. In a standard Hall effect sensor, it just measures magnetic flux along one axis. A 3-axis measures it across 3, X, Y, and Z, up and down. The reason they do that is because inside a cell phone, you could be holding it in any orientation and you still want to be able to detect true north or magnetic north through the sensor. By having 3 off-axis sensors, they can do math and determine how the phone is oriented and deal with the numbers and figure out which way actual north is, regardless of how you're holding the phone. Where I think that's going to benefit here is with a standard Hall effect sensor in this pump body, how you orient the sensor to the meter is vastly going to affect how much of a signal you get out of it, and even optimum, it's not going to be that much. Using a 3-axis down here, it's much more sensitive, and I bet that the field, the near field, magnetic field of these magnets is going to be much stronger than the Earth's magnetic field. The other thing is with 3 axes in this sensor, you could stick that on that meter any which way you want, and one of those 3 axes is going to have a fairly good detection swing of the position of the magnet. Actually, in this microcontroller, you could probably come up with an auto-calibrate routine that would monitor all 3 axes for a minute or so and figure out which one has the biggest swing from the highest number to the lowest number, choose that one to do all the future measurements, and determine a switch point where you're going to decide, okay, when it goes below this point, we've completed 1 revolution, and that could be totally automated inside the microcontroller. The only problem with the 3-axis sensor is that the thing is absolutely microscopic. You probably can't see it on there, and there is absolutely no way you can hand solder this device. Luckily, Tautic of Jason Tautic, who owns Tautic.com, sells this nice little breakout board, the parts installed with the caps, and it's ready to go, and I don't have to figure out how to solder that little thing on there. So this is the sensor we're going to try first time out with there. The other part, the radio link, I got these from SparkFun. They're real inexpensive, $3-4 each, is a transmitter and a receiver, 315 megahertz I think. It's ASK, which I believe is amplitude shift keying. Basically, you give it a power ground, send data in one pin, and it comes out the other end. But obviously these are still in their little plastic bag. I haven't tried it yet, so that remains to be seen. For the microcontroller in here, you could use an Arduino or any microprocessor board you come across, but since we have to run it off batteries, it has to be very, very low power. So what I've decided is I'm going to use a little 8-pin PIC microcontroller. Like I said, I'll have all the part numbers for these below this video entry. This 8-pin PIC is very, very low power, and internally it has a bunch of peripheral devices, which is going to make interfacing to this other stuff very simple. For the initial prototype, I'm using this board, again from Tautic Electronics. I've used a bunch of these in a bunch of other projects, and it's a very handy board. It gives you the 8-pin PIC, a little prototype area, the reset circuit, and the header that plugs right into the programmer that comes from Microchip itself. And so in the prototype, the only real external thing that's got to go on here is going to be that transmitter. That'll fit. I'll need a voltage regulator and maybe a couple other components. They'll all handily fit down in that prototype area. By the end of the project, I'll spin my own printed circuit board for this, probably go down to an SMT part or something, but for now, this proto board is absolutely ideal. So there's our sensor, the microcontroller, and the transmitter. The only thing left is the power and the battery pack. What I found at Harbor Freight is a solar-powered, motion-detecting LED security light. It's got a 60 LED array in there, a motion sensor, there's a battery pack in there, and the photovoltaic panel. With my coupons, I picked this up for about 25 bucks, which may seem like a little bit, but for 25 bucks, here's a solar panel, all hermetically sealed, weather tight, ready to be installed outside. In there is an 800 milliamp NiCad battery pack, which will work very handily with all this. The motion sensor and the LED lights, some other project down the road that'll get used. And I can also, when I tear this thing down, figure out how they manage charging the batteries and switching and load. It's cheap Chinese stuff. My guess, there's one diode that just does that. But the thing is, we can take a system that we know works and get the entire power system for our little project. So basically that's it. So the first thing I've got to do, the first question mark that comes up is this sensor. It's an I2C interface back to this microcontroller. I don't know what kind of numbers I'm going to see. I don't know how it's going to be positioned around this pump. There's just a whole lot of question marks. So the very first thing I'm going to do is take the little PIC board, wire up an interface to the sensor, put that to a display, and just give it a battery pack. What I can do with this is make a small, easy-to-use device with the sensor and go sit out next to the street, next to this water meter, and move the sensor around. Make sure I'm accurately reading data off it, see what kind of number values I get off the meter as it's going around. So that is step one. There, and our little sensor. Hopefully the next video I'll be able to show you this tool to evaluate sensors. And actually, if this sensor doesn't work, I can still use that tool to plug other sensors into it and see what will. So in the next video, I hope to have that all put together and show you how that works. We'll have figured out how to interface to this sensor. We'll know what kind of numbers we want. And from that point, we start playing with the radio transmitter and get the data back over to the far side. If you find this interesting, I hope you follow my project. If you found this video on my YouTube channel, follow along on there as well. And hopefully, next time I post a video, I'll have blinky lights and things happening. Should be a lot of fun. Thanks for watching.